So hello, welcome. I am today going to build a playback module using Gen. I want it to be able to play back and sample from a buffer, from really tiny snippets to longer sections with a high degree of accuracy and efficiency, to the point where it could be used as the engine, playback engine of grains for granular synthesis type thing, or concatenative synthesis. For my purposes, I'm going to be implementing it into my older computer improviser called the Scuff computer improviser, but also for my current projects that are using the Flucoma libraries. So I want to be able to send it a start time, end time within milliseconds, gain, playback speed, and the window coefficient. Great. And I also want to include panning controls. So there'll be like, 0 to 1 in a stereo field, and random pan option. Okay, so to get started, let's create a buffer, and I'll name it sample buffer. Read. I'm going to read it 2-piano piece called distances, and it's 2 microtonal pianos. So I have this in my buffer. It's stereo. I want to be able to do stereo playback as well in my Gen object. So at the outset, I want to think about how I'm going to format this message. So it's just going to be a list. So say I wanted to play it back from 10 milliseconds in, or 10 seconds in, 10,000 milliseconds in, to 11 seconds in, and I want it to be full loudness, regular playback speed, and let's use a 0.5 window coefficient. I'm going to be implementing the 2-key window, so a 0 is a sine wave, and a 1 is a very trapezoidal sort of flat top quick slope thing. Great, so that's my message that I'm going to be working with. So I know I'm going to want to unjoin that message into its 5 parts to send to my Gen object. And I'm also going to want to have an input in the Gen to say, start the sample, start the windowing. So I'll need to include that as sort of my final message. All the settings are set, and then the final message of go. So for that, I'll just use trigger bang float for my final one there, and I'll use click object to trigger in Gen. And I'm using the click object because it just sends a one sample impulse that Gen is able to interpret kind of like a bang. Sort of the Gen equivalent of a bang, because everything's always moving at a sample rate. In Gen, you don't have data at all or bangs, which can be challenging sometimes. All right, so let's make our Gen object. We'll open it up. It instantiates it as it always does with just a simple addition. You're gonna get rid of what's in there already, and I know I'm going to want to have an input for each of these pieces of data there. So input 1 will be at comment start, or let's say trigger is a little bit more clear. My second input at comment start time in milliseconds. My third input will be end time in milliseconds. My fourth input will be my gain multiplier. My fifth input will be my playback speed multiplier, and my sixth and final input will be my window coefficient. Oh, and input 6, of course. Great. And I'm going to want to have 2 outputs because it is a stereo sampler. And I'm going to just make a 3rd output, which is going to flag when it's complete, which will be an important thing to have when I wrap it up in a Polytilda object so that I can really put it to use. And then we'll have a final 4th output that will delete at the end, which will be for debugging and showing progress and sanity checks on the way. So let's plug everything in here. So there we go. Start time, end time, gain, playback speed, and window coefficient. Okay, so we're going to be sampling using the peak object, which peaks into a buffer. You give it the buffer sample index, and it reads that. So in order for that to work, we need to have the buffer on the inside of the gen patcher. So we've called it sample buffer. So if we double click it, yes, there's our sample, very good. And this can just be wherever, just have it out of the way. And then peak, and we want to peak our sample buffer. So read the samples back from the sample buffer. I want to have interpolation on. So if I ask it to read sample 1.5, it can interpolate the data from between 1 and 2. And we're going to do that in a linear fashion because I believe that's the most efficient way of doing it. And I can't really hear the difference between the different types of interpolation personally. Maybe at very slow playback speed, it probably makes a pretty big difference. Or if you're using it for not for generating audio or playing back audio, but for say I don't know, if you have wave shaping or something like that you're doing with buffer data. In any case, peak sample buffer interpretation linear, and I also want to change the bound mode to wrap. So if I ask it to read something out of range, it will wrap around. Great, and so I'll have that coming out the first outlet, and we're going to want to have a second one of these, and in the right inlet you have channel offset, and it's 0 base. So if I give it a 1, it's reading what we generally call the second channel. So this will read the first channel, and this is the second channel. So out 1 and out 2 there. So now to read the buffer data using peak, we would need to send it sample indexes, so that we could use a counter, have it count 1 sample per, increase by 1 per sample, and so it would sort of read that at a regular speed. A slightly more efficient way to do it is using the accumulator object. This object, it has a reset and it has the amount to add. So the amount to add will be, well, just as a test, let's just have it be 1. So it'll read 1 sample per sample, or increase by 1 per sample. And let's have the trigger reset the accumulator, and let's send it to our debugging outlet here. So let's make not a button, but a number box, signal number box. And so yeah, it's counting up. And every time we send it a message, it should reset the counter. Yeah, very good. So if we plug this into peak, and we have a meter here, there, we see it's playing back. So let's actually listen to that. DAC 5 and 6 for OBS. Yeah, and it resets every time. Great. So that's the basic playback function. We want to be able to sample both forwards and backwards and at different speeds. So in order to have it go forwards and backwards, we would like to have a switch that will switch between forwards at 1 and -1 for reverse. So it'll get that number, it'll know whether it's playing forward or backwards by calculating the difference between the start time and the end time of the sample it's being asked to read. So if it's 10,000 to 11,000, it's forward. If it's 11,000 to 10,000, it would be backwards. So we can do that using the less than operator to test between the difference between our start time and end time. And so if we do that, it should be reading forwards. Yep. And let's change this to 12 so that It's going backwards, and it indeed is reading backwards. Great. So our accumulator is working forwards and backwards as we want it. So now we want to be able to control the playback speed. So for that, we just need to add a multiplier in there. So let's use the multiplication object, take the accumulator value and multiply it by the playback speed. All right, so we can go ahead and test that. Should just be playing back normally now. But if we send it a playback speed of 2, playing twice as fast, at 0.5, half speed, and it's interpolating here. So that's where it wouldn't be working properly without the interpolation in the peak object. Great. Okay, so next in line, we want to be able to give it the start time so that it plays from not just from the beginning of the audio file all the time. So that's a simple addition. So because we're working sample rate and I've asked for milliseconds here, we'll need an ms to samps object going here, and then that goes into here. And so now it will always play back from whatever that first number is. All right, so let's test it. We'll have it play in reverse. Play it from 1 second to 2 seconds. Great, it's working. Now we need to also connect to this one for stereo playback. And I'll just add another meter there to monitor it. So now we'll be playing back in stereo. And from here, we need to now window the audio. Okay, so to do that, I'm going to bring in a windowing function from this book, Generating Sound and Organizing Time by Graham Wakefield and Gregory Taylor. So this book comes with a package of externals, or not externals, but sort of pre-made bits of code in Gen that are designed to be used creatively. And so that's what I'm doing here. It's a great book. I can't recommend it enough. And it's been fascinating to go through the materials that it comes with and reading it and learning from it. So what this does is it's a windowing function. So let me just show you. So this is one of the patches that come with the book. And so I won't go in there because I don't want to sort of give away their code because it kind of comes with the book. But I mean, you can see a little bit of sample of it here, but you can see the 2-key function here. And the coefficient changes the shape. So you see this one is more trapezoidal and this one is more sinusoidal. If the function, it's scaled between 0 and 1, as 0 is purely sinusoidal and a 1 is totally flat with very, very little slope at all. So that's what I've implemented here. And so you feed it a unipolar triangle and you give it the shape coefficient in the right inlet, and out comes the function. I will just bring that as a Gen subpatcher in there. And so what I need to do is multiply the outputs using this windowing function. So for that, I'm going to need to get the duration of the, as in the difference between the duration of the sample by looking at the difference between the start time and end time. So to do that, let's subtract. We're going to subtract the start time from the end time. And so now that data is all in samples. No, I'm sorry. We want it to be in samples. So that data is in milliseconds. So we need to get it in samples. So we'll use milliseconds to samples here. So let's just test that. So right now it's 1 second long, so we're getting 48,000. So we want to get the absolute value of there. So whether it is a positive or negative duration. We want it to always be an absolute value. So let's just double check that. So 48 and 48. Yeah. So on 96 if it's 2 seconds long. Beautiful. All right. So we have the duration of our sample here. Now we want to get the absolute value from the accumulator because we can't be reading our function backwards. And we also need to, and so then we need to divide the count with this duration so that this scales up between 0 and 1. So let's just check that, right? So it scales it between 0 and 1, but of course it keeps counting. So that's something that we are going to fix by clipping it between 0 and 1. But before then, we do want to take into account the playback speed multiplier. So we will do the same multiplier will be applied to the window as to the sample playback. Clip it between 0 and 1, and let's see what we get. It should just stop at 1. Yes, perfect. So this will be used to drive the triangle. So this is our unipolar triangle that drives a windowing function. So I stick it in there. We should now see it go from 0 to 1 and back down, right? It's our triangle. So we could even just window it with the triangle if we wanted to, but we're going to use this triangle to drive the function here, and we're going to put the window coefficient in here. And now we should see it. Okay, it's only going from 0 to 1. So why is it not going back down to 0? Let me just double check this. Oh no, it is going back down to 0. I just wasn't being patient enough. All right, so we now see the function going up and down. If we put it at 0.9, you'll see it just goes up very quickly and then back down very quickly at the end. If it's at 0.1, it's basically sinusoidal, goes up very gradually and then back down. Great, so we have our windowing function. So all we need to do to window this sample now is multiply the outputs. So there's our first multiplier, there's a second multiplier, and put our function into there. We don't need to debug that anymore. So now let's listen to it. So you see it's not just playing infinitely now. Great. Right, so let's do a reverse sample. Right, so it plays forward and reverse. So right now it is taking the windowing function, the playback speed, but we haven't done the gain yet. That's very simple, of course. We just need another multiplier here. Or I'm gonna disconnect this so we don't hear it every time it instantiates. So our gain multiplier at the very end. So I'll just bring that down here. There, so that's very simple. So now we have it completely finished, except for our panning. And except for the panning, except for the trigger that says when it's done with the sample. Great. So let's do the trigger to show that it's done sampling, and then we'll finish with the panning. So for the trigger, I basically want it to be that it's sending out a 0 out of the third inlet whenever the windowing function is also giving a 0. So if it's basically, I want to know if it's audible or not, if it's sampling audibly or not. So for that, we're going to ask the gen object, we're gonna see if we're getting a 0 or not coming out of the windowing function. If we put it out 3, put it to here, right? So 1 when it's audible, 0 when it's not. And yeah, that's all we really need. So we have our on and off. So that'll be useful when we turn this into a, wrap this in a Polytilda. Okay, so now the panning. So for panning, we're going to use parameters. So param, let's just do the pan first. Put at default as 0.5, which is in the middle of the stereo field. At min will be 0, at max will be 1. And then we're going to have a second parameter, which is our random pan. Our default will be off. A default will be 0, and then any non-zero will turn it on. So basically, you could use a toggle to have it going. Now, so I'm going to do this by using a switch. So I want to be able to switch between randomness and this controlled pan. So the controlled pan will go in here, and we have it between 0 and 1. And so for our random function, actually, hold on. I'm going to want to have the random function in the middle one there. So the random function, I'll use noise. Noise generates every sample somewhere between a 0, a -1, and a 1. So we're going to want it to be an absolute value. And we're not going to want it to, we're not going to want it to change. We're not going to want the panning to change wildly every sample, of course. So we're going to want to use a latch, which is kind of similar to sample and hold. So it will hold the value of the noise object until it gets a non-zero in the right inlet. So if we use our trigger to unleash the latch, then put it in there, that should work. So if I go to test this, every time I hit the trigger, I should get a different value out of there between 0 and 1. Great. So that's our random panning, though every sample we pan differently. And then our controlled panning is there. And so to actually do the panning, again, we're going to need a third and final multiplier for each of these. Let me make sure everything's still visible on OBS. Yeah, good. Nothing's blocked. So we're going to need another set of multipliers there. And then we're going to use a Polytilda to calculate the panning. So to do that, I want Polytilda, so polar to Cartesian coordinates, and the angle. It'll take the angle between 0 and 1. And then we just want to give it a 1 as the polar radius. And then that will be multiplied the x and the y. So in order to get the Polytilda to work, I need to multiply this value between 0 and 1. And multiply it by half pi to sort of scale it correctly for the Polytilda. Okay, and now I need to actually control the switch using this random pan. Right now it's just the randomness won't turn on. So that random pan is going to control the switch. So if random pan's at 0, it should have the manual panning. Great. And if I turn random pan on, and it should just always play back in a slightly different spot. Great. Super. Okay, so that is my playback object all done. So let me just clean it up by getting rid of my debugging outlet and putting my trigger there. Just clean this up a tiny bit. And now the task will be to turn this into something that can be wrapped into a poly. So for that, I'm going to need an inlet for the message. I'm going to want a second inlet for the pan value, and a third inlet to turn random pan on and off. And then I'm going to want two audio outlets for my output. And now to have it run efficiently, I'm going to want to use to mute it or unmute it using the this poly object. So get this poly, and let me just open something here to make sure I do this correctly. Yeah, okay, so it should look like that. Great. So you want to use these messages, mute change from 0 to 1, so that's to turn it on, and mute go from 1 to 0, so that's to turn it off. So by default, when it loads up, we're going to want to turn off the poly, and then when it's called upon, turn it on. So how do we know it's called upon? Well, when it gets this bang, which is the trigger to start everything, that can turn it on. And then we also want to turn it off when we get a 0 out of this. So we can just get a select 0 out of there. Now this is not going to be sample accurate, but it will work just fine. So it's off, it's on, it's off. Great. So that will turn it off. Now, for whatever reason, a gen object within a Polytilda will not see the buffer within the Polytilda object. So what we need to do is to have this buffer be an argument. So in the Polytilda object, we'll do @args and then name the buffer. And then we'll need to send a message that renames the sample buffer. So it will look like this. Sample, hold on, actually, let me double check this. Right. Sample buffer, which is what we've called it inside the gen object. And we're going to rename it or refer it using that argument. And so that will also need a load bang to make it work. All right, so now this is fully set up to be to be put into a Polytilda object. So let's go ahead and do that. So I'll open up a new patcher here. I'm gonna save it in the same folder as playback module. So playback module wrapper. And we'll go Polytilda. It's going to be playback module. Let's give it 128 instances. And @arguments sample buffer. Let's just use the same name. All right, so if we go in here, we see sample buffers there. So now we're going to want to have the buffer here. Sample buffer. Oh, and in fact, sorry, I've made a mistake here. I don't need the buffer in here. In fact, it shouldn't be in there. So let me save that. Go back to my wrapper. Hold on, where is it? There it is. Okay. So I'm just going to reload that. Okay, good. It looks how I want it to. Buffer, sample buffer, and I'm going to read that same sample into it. And there it is. Okay, let's make sure that that has loaded properly into here. It has. Great, it's the same sample. So now to get this to work, I could send it the same kind of message, but with note in front of it, so that it finds a version that is not currently working, or rather an instance not currently working. And let's get our DAC 5 and 6. Now one thing, oh, I see what I did. So there's one other error here, which is my outlets are not 1 and 1, it should be 1 and 2. Save that. Let's open our wrapper back up. There we go. Oops. Let's get a couple of meters and our outputs. And beautiful. So now I have it fully working. And if we look at our CPU monitor, even with that running, I also have a second sort of thing running on my second screen. It's still very low. And if I were to use it, just spam that, it would still not really drive the CPU up much. Right, so it's very, very light. So it could be used for granular synthesis, concatenative synthesis. And then the final thing I'll show you is just sort of one quick implementation I did of it, where I basically took, let me close it here, save it. I used a couple of Lorenz attractors that were also from this Generating Sound, Organizing Time, Graham Wakefield, Gregory Taylor book, and I scaled their outputs to be a sort of quasi-random start time, quasi-random duration, and sort of rate of attack for metros, and then use the sprint the sprint f object to format the messages that I send. So I have this poly object that we just built, and you can see it can handle quite active playback, and it really doesn't strain the CPU at all. So yeah, I have one doing reverse samples, one forward samples. So that's it. I hope this has been useful. In the future, I will be using this in all sorts of projects. I hope it's been educational and will be useful for others as well. Okay, signing off.